Welcome everyone for Cloud Computing and Big Data, our lecture 4 on virtualization and data center design and the second part of it. So the first part was really reviewing a little bit on, virtualization, a basic technology, if you want, in computer science and computer engineering today. So we didn't cover all the basics, but the general idea of terminology, virtual machines, virtual appliances, hypervisor, and so on, we reviewed again for those of you where this, basic knowledge is maybe forgotten a little bit. But of course, there's much more to virtualization that we could cover. However, for us in this course, it was important to understand that the same principal ideas that we took from virtualization, on your little laptop or on your traditional computer, PC, etc., we basically moved from this to larger and larger data centers. And in the second part here now, we will pick upon some of these concepts, but also put it in the broader concept. So basically, we will see how a data center is also created, second floors, gas for, fire protection and whatever. So these are all concepts where, this is sort of the 80% mainstream data centers, while the data center design today can be really vary. It also obviously is very related to where the data center is. So one example, Lumi, Kajani, one supercomputer in the Union is essentially in Kajani, very much up north in Finland, with lots of ambient air cooling, cold areas. And still the data center is designed in a way to fuel with the waste heat and everything which comes out of it, a whole district next to it. So other data centers might be close, to some other, let's say, spot where you have maybe hydropower resources. So long story short, even if you're in countries where obviously ambient air is hotter, there could be also warm water cooling. There are lots of different concepts that I cannot, let's say, all go into detail here, just that you know that the cloud data center design are some principles that, stand the test of time. And as this community is really flourishing, right? So we see data centers growing not only in Iceland and the Nordics, generally around the world because we need them. So basically, this means there are more and more specialized data center designs also for the scale we're talking about. So let's go a little bit with the data center design then in terms of principles. And again, we have to start a little bit from terminology. So some of you know that already a bit from the high-performance computing course, but here we will look at this again. So many of you know that there's usually here and there some servers around. Universities, larger organizations will always have some servers, that give multi-users already some, development platform or something which they host there, for instance, data, which is relevant for the analysis within the company. And this is something which, where it all starts from. But when you come to a more professionally hosted data center, you would say it's not like you just put these servers and put them all in a row and then you have a whole room full of, this smaller servers running around. So basically, we're talking about racks at a certain number of scale, right? And in one respect, this interesting graphic that you always have seen abstractly with Apache Spark and already earlier in the course is a bit representing this, right? So you basically have lots of these racks, which are also lots of servers in, but they're much more condensed. There's much more compact designs these days, right? That you have available in these racks and the better concept for cooling, overall we will look at and so on. So, and these are very well interconnected as well, right? So you will see in one of the videos and one of the pictures, of course, a network interconnect is another important principle, making these racks really tightly integrated and then enables really something we call economics of scale. So you fit much more in a data center and so on and so on. So this is important to realize so that on this scale of data centers, you're not talking about smaller servers usually anymore. And I think we see how that, materializes when we will do the visit in one of the data centers within the course. They have lots of racks, while the applications within it might be very different. Might be basically just one customer that has a rack in a data center, very secured, and runs his operations, while another rack or a couple of other racks might be multi-user. So many users from different organizations are using it. So of course, the racks are basically an abstract principle to say there's a condensed or really compact way of computing and storage available in data centers. So, and this enables then also the scale. And I think here you see the scale we're talking about now when we also have our left picture again from the Apache Spark, right? So this is one example of a data center, right? So this is something like around 1 million servers, somewhere around this, in this housing of 11 times a football field, which gives you sort of the indicator now how sizes are there and what we're talking about. And you see here the space, the floor space, as we say, there are multiple racks here and there inside storages. You see also something what we call the DRUPs, so diesel engines, and basically probably the fuel for the diesel engines in case the electricity goes off. The data center can operate a little bit more, but in an increasing size like this, it's getting more rare that these can actually operate without electricity very long. So the operators we will talk about also in the second part, are more and more, let's say, limited by the scale. However, this is of course really something where economics of scale is essentially the term, because here you would have that, the larger the data center is, the better it is, the lower the operational cost. You have the whole infrastructure there, the cooling infrastructure. We talk about what infrastructure means in a minute, but there are lots of different aspects to it than having, for instance, let's say 11 times, this data center. Let's say each one of a football field, where we say we have 11 data centers, that this one big one here, but they would operate not on the same economics of scale. There would be, the infrastructure is helping here to realize this concept. And this means for cloud computing providers like Microsoft and others, having then 100 of such, large and small distributed around the globe, that they can, work on a much lower operational cost, right? So this is an important takeaway message. That's why there's a move towards greater and bigger data centers, because they're basically cheaper to operate. So how this works now to use this, let's say, in a maximum utilization is again our virtualization example. So within this big building you have seen, which we abstractly model as this aspect here, where you maybe want to run Apache Spark on, right? Do you have many different physical servers in a row? No, these are basically modeled like this, but the way how it's used, it's actually quite different, giving our virtualization design. So you have virtualized clusters that could be essentially modeled in different ways. You see one virtual cluster maybe, stretched across different 3 physical ones. You have one virtual cluster maybe dedicated to each of those. So it really depends, also using just part of it, just showing you that there's a lot of flexibility in this. And this, of course, drives now the utilization, because users have different requirements, which VMs they want to host, which of their applications need a very high uptime. Let's say a physical cluster would go down because of network issues. Then you see that this virtual cluster will fail, or it would be live migrated maybe, but still, have some issues, while this virtual cluster can have maybe better uptime, having some of the applications replicated on different physical clusters. So there are different properties. And if you have here, for instance, the Apache Spark again, you would say that if you remember a little bit from lecture 3, right, we had the head nodes, the worker nodes, you would say that the virtualized cluster we talk about can be also extended, like virtual cluster 2. Could be here that we have a head node, we have 2 worker nodes, but if needed, we can expand the virtual cluster to this free space here in a data center and add more 3 worker nodes. I mean, in a very abstract notation now, but again, coming to the shrinking and expanding concept of a cloud, right? And this is fueled by virtualization. Of course, you would say it's also limited by the physical availability, right? So if you say Spark again, and now I have a super duper job, I need 1,000 worker nodes, let's say in a cluster like this, which is already fully loaded, then here you go, there's just no availability of 1,000, right? So Hence, you would maybe consider to go to another data center, or maybe even stretch your offering across different data centers, right? So obviously, at some point in time, even these large data centers are just fully loaded, and in a way, that's also their goal, right? Of course, they always provision resources in a way that users can add resources, also on the principle that some others maybe remove resources. And there's concepts like over provisioning here and there to keep the utilization and so on, really in a manner that it's for them a very good return of investment of these big data centers. You don't want to have a whole data center empty and just waiting for some users to add 1,000 worker nodes in Apache Spark. So these servers should be running 99.9%. So what I said to you, 100% is usually very tricky. Because of standard maintenance already. So every now and then you will see that some of the physical clusters need maintenance. You maybe have to renew some of the kind of rack parts. So, but hence this enables us also this scalability we were talking about earlier, right? By using Apache Spark, the resources have to come somewhere from. And by partitioning this with applications, across also different application spaces, multiple users, these data centers can now serve different application communities. This is a very important part as well. So hence they're not only multi-user, they're also let's say, application domains. In a way, everybody can use a data center, so to speak, right? No matter what applications, the important thing that it fits somehow in a VM, and you can use virtualized resources in a way, and computing power. And you know that already from a little bit the starting of the course, where we have said some requirements for neural networks will be GPUs. So some virtual clusters offer then nodes for, let's say, application A with having some specialized GPUs that we want. And some others have maybe even cutting edge GPUs where we have to pay a lot, but it's not needed for everyone, but for some. So you see also, this is something where there's a flexible demand, but there's also flexible offer. And if you see that later in our lecture, we will come and review this a lot, that this is, of course, directly related to the cost, right? What you want in terms of GPU A, GPU B, you go there and pay the price for it. So other concepts here is, of course, the operating systems we already discussed, but also the replication scheme. Something we will also review a little bit in the next lecture. Basically, when we come back to, basically data needs to be fueled to neural networks and so on. But also way later when we talk about MapReduce, Hadoop distributed file system, that you have a replication scheme of data around. And this, of course, helps also for the uptime, disaster recovery. Let's say really one of the data centers will completely go off, then we would have the data maybe with replication in another data centers, and users can still work on the data. So hence, this is, also from the application perspective, very flexible, often used. And in this sense, with combining then these different loads of applications, you usually get with this wide variety of cloud, tools, services, applications, a very high server utilization of your data center. And this enables us then as data center operators to really, offer these services on a, let's say, relatively okay price, because we have to also think about that in some occasions, if you really need that computing, you can go ahead and create it your own, right? What would that entail? You would need a cluster somewhere in your cellar. Okay, that might be not cooled enough, so you need a cooling infrastructure. Okay, the network connectivity might be not good enough, so you need a better network. Well, then maybe not everybody should enter the cellar overnight and gets all the data by stealing, so you need a proper protection mechanism. You can go on and go on that. Of course, we know that the price for a GPU can be quite high, let's say $24 for 1 hour. But then equally, you have also an infrastructure problem if you want to do it your own. For some occasions, this might be viable. Let's say hospitals that host patient data is a very common use case where you want to have maybe the servers in-house, right, on a still very protected way of, having this in-house. But this comes for a price, and this is, of course, something we should review a little bit. And it's a bit shown in this slide here, where you see the fixed costs in the capital equipment that you have to buy, right? And in high performance computing, cloud computing, this, let's say, every 3 to 5 years, where you have to rebuy or update your cluster, is maybe not anymore completely accurate. I would even say these days, if you see the NVIDIA GPU generations, going from Kepler and Ampere, Grace Hopper, now to Blackwell architectures, which is a cutting edge. This is not anymore, you would say, even every 2 to 3 years, if maybe every year in some of the applications, need to be an update of your fixed costs. So that means basically, if you put it in your own data center, in your own cellar, after 1 or 2 years, your GPUs are already old, or your network interconnect is not anymore up to date. Or, you can come up to many examples where you see that these days, the IT technology is moving at an unprecedented scale in terms of performance, in terms of availability, potentials, right? So if you see about what NVIDIA can do with tensor cores versus what we had 20 years ago with CPUs, and then slowly coming up with better CPUs, GPUs change the whole idea, the whole setup. So this would be another fixed cost. And then within even the GPU, the generations matter a lot. More HBM, high bandwidth memory, changes the story for lots of different applications. So you can go on and go on that essentially what you as a user will earn is that you basically have just the variable costs in the operational expenses when you buy cloud computing resources. Right. And this is something where this cloud computing cost model comes in, and which makes it so attractive for several people, in the industry to really go there. And then once they have tried it, once they have looked in it, stay there and even scale out. So this idea was born in that fact of saying, just pay what you use, right? So the cloud provider, Amazon, they care about, okay, getting new GPUs and offer it for you, and you just pay for using, right? Swipe the credit card, so and so much per hour. So this gives you, of course, then, especially, let's say, for SMEs, smaller, medium enterprises, startups, really smaller companies, a really nice opportunity to tap into that computing space, which would be otherwise not possible, right? You cannot just create quickly with some startup money a big data center. And if you need cutting edge AI, you need this, let's say, large language models will be also will review very soon in the course. So this is something where this not upfront cost is then, or was in a sense, also another breakthrough of this cloud computing cost model, right? Where a little bit more in comparison maybe with grid computing, which had similar ideas, there was never really a cost to it. And basically with this, industry commercial partners really had an idea of how to really run a data centers, make profit, because others had a win of not anymore have to spend the fixed costs and could turn that into the variable costs. And with this, of course, shrinking up and down. So when you then look on infrastructure costs, and this is something which varies really from large to small data centers, it really depends on which region, which geographical, location you have. I was alluding to Lumi, for instance, which is, the data center or the supercomputer in Kayani, way up in the north, is completely different of hosting it somewhere, let's say, in the middle of US. So there's one thing that always goes in common. You have to spend a lot of thinking on cooling, right? So hence you will see some statements that many of the data centers, their main concern is cooling. So chilling, cooling is quite some costs for the data center. Hence, you can understand why many people go to the north, right? And why at North Borealis data centers here in Iceland and maybe even Verne, and they're all located more or less in Norway and Finland, and you go there in Iceland. So basically, this north of ambient air cooling, of colder climate, is of course something important. Then the whole aspects on electricity, right? Power distribution and so on is also something what you have to do to think about, especially when you want to have emergency power. This is needed to keep your SLAs, your service level agreements, right? Especially if you think about that, there's suddenly no electricity, you want to keep the applications running. This UPS, so diesel engines and so on, can at least for a couple of hours, generate enough electricity to keep some operations running, which is a matter then of your SLA negotiation. But this kind of element is something where infrastructure costs also play in. And of course, then the costs for the IT equipment is another factor. And there we have seen that the increased costs over years is now definitely related to more and more GPUs, right? Cutting edge GPUs like, the Grace Hopper chips or things we will also later look up in the course, but then also Blackwell perhaps now, right? So these cutting edge NVIDIA chips are enormously expensive. So also this IT equipment is costly, but don't forget that we also said many of these racks are interconnected with good network equipment. So it's not only the data center has a good network, basically it's within the racks, very high bandwidth connections, which is also very costly. So also coming back to the IT equipment, combined then maybe with computing network, you have, of course, storage, right? So storage these days is also something where you have to think about, you want to have active storage, not tape archives where you have to wait a long time to migrate that out on a disk and then work on it. You want to have basically active storage. And this is also something to review in the course here a little bit more in the couple of next lectures when we come to it. So, and many of the things I have already said to you, and this basically the interesting thing is then to think about that the allocation to management and the maintenance of all these infrastructures, I think, is here the 60%, right? And this is something where this varies obviously again from data center to data center, but this is also now something where you have to think about when you are in a company, do you really want this? Right? So the data center running itself is a business, and that is often overlooked these days. And I here don't even mention certifications. We will review this briefly with the Borealis data center coming in one of the slides now. But they have lots of aspects today that really says that data centers is a business. So hence Borealis, right, is nothing else than hosting data centers as a business, but being professional in it. So when you are in a company and you want to do it on your own, you really have to think there's lots of costs related to it. Plus, of course, what we said, the electricity location aspects in the north, where to put it, etc., etc. Good, but I think this is explaining also more and more, with the costs, why Iceland is more and more attractive. And I have here a video. I don't play it because of YouTube. I don't want to have a problem here in copyrights or so, but I encourage you to look at this video, Data Centers by Iceland, showing you all the benefits, from this. We work closely together with the data center industry in Iceland. As I said, my students regularly go to the data centers to touch metal, but also we do lots of events together to promote Icelandic data centers. Of course, you see here some of the data centers in Iceland. Some of them, they're very well known as at North and Borealis, perhaps also Verne Global. And they all have some cloud offerings here and there. So it's also something to understand. There's also some application business part, or if you go to Borealis or Rigo, they have some responsible compute joint partnership, enabling more in towards the application area. And you can imagine that with this, you have, let's say, already idealized conditions. But what we didn't touch upon yet is then, of course, this green energy movement. Now, needless to say that, data centers in Germany don't have so much geothermal resources, don't have so much hydropower resources. This is still a lot of coal, right, behind it. And of course, there's a movement now that, essentially in the next years, more and more, this should be transformed to, green and clean energy, which is for Iceland absolutely not a problem. No, this is, 100% of Icelandic's electricity is really a mix, if you want, from geothermal, hydro power, and so on. So this is then not only the ambient air cooling, which is a benefit here, but you can also say that in the long run, you have green solutions. And I just want to give you another example here. So as I said, we not play the video here, that you have lots of benefits of thinking about this. And when we then come to maybe some of the data centers, even just to say here, they maybe even duplicate resources. One of the data centers we work with, for instance, in our commercial partners, again, from Borealis data centers in Blöndos, they're close to power plant there, but they essentially have two different independent hydropower resources in a way they can tap on. So this gives you another, let's say, protection mechanism of having green and clean energy, not only from one source, from many. But yeah, I stop here in the moment just to, again, thinking about also the green aspect from another point of perspective. You will see that with NVIDIA GPUs, the efficiency really and the performance and they would say performance and power ratio, if you think about the flops, the floating point operations per seconds per the watt it takes, is also something which has been improved more and more. So you would say from getting 20 years ago from the CPU, with caches, memory, and this is now with the optimized throughput in GPUs quite interesting, because the power consumption is essentially something which is getting very green in a way to these NVIDIA GPUs, but also other GPU architectures. So there's also a sort of movement when you think about this, cutting edge CPU, high single thread performance, the power requirements. So this is also understood that with GPUs, which perhaps was fueling also a bit the advantage, right? Why GPUs are suddenly so in vogue is also that it is basically quite a good power efficiency as well. And this goes along, and here's a nice area of, having the Kepler architectures up to Pascal, Volta architectures, Ampere, and as I said, the hopper chips and Grace hoppers and so on. And here what's missing is a bit the Blackwell, which is now there. But I mean, they are all getting more and more powerful, of course, in this sense, consumer power, but you have to also think on the ratio, right? How much computing you get, so flops per watt. And this is quite an interesting factor. So another facet we have to talk about in this larger data centers is then that you assume failure by design. What does it mean? So you see here a quite interesting whole of a Google data center. Which one doesn't matter? You have tons of these racks. You have the infrastructure, up here, here with all the cables interconnecting it and so on and so on. So with this amount of hardware, and you would say maybe, as we said, 11 times football field as the other example there. On this scale, you can assume that there will be some CPU failing, there will be some storage failing, there will be some network problem. This is always happening, right? So you have to scale in this area, and by providing more computing, you also have to swallow the drawback and say hardware will fail. It will overheat. There will be other problems. So hence, again, the idea is that all of these data centers today, they operated with this in mind. They have already mechanisms in place, and we will talk about, for instance, just about HDFS, how you do data replication with some software, that you can use Apache Spark with, for instance, so that you can use a computing, basically still, and the failure situation will be automatically, recognized, and perhaps your job, your application will be automatically using data from another data center then, or your job will be relocated, or we have this, live migration of a VM as another example. Your server will be automatically starting the live migration and your operation is working again. So Apache Spark, for instance, has many of these functionalities inherently in the design that, basically it will work with these kind of errors. If, of course, the data center is prepared for this. And this is just something that you really have to know by heart, that these large data centers will have problems. So when you have then these errors, and one of these big errors could be that there's no, let's say, power. We discussed this already before. That is called DRUPS, diesel rotary UPS, standing for uninterruptible power supplies, UPS. And you have them usually a couple of those close to the data center, and there will be somewhere a kind of, probably small tank for fuel very close to it. And the idea is here that, as I said, when there's no external electricity coming into the data center anymore, for some reason, could be whatever, cutted lines, could be a reason where, of course, a data center is not responsible, but they are responsible to their clients. They have to respond to SLAs. So in this sense, they do everything basically to really, basically operate these UPSs. At the scale we're talking about more and more, we have exascale performance now, even in Euro HPC, right? So starting with this large scale, with the consumption of having thousands of GPUs and lots of CPUs alongside. So it's getting more and more, let's say, a bit unrealistic to have so many UPSs close to it so that the crash can hold for many, many hours, right? So usually it's not really a long-term solution. I mean, in theory, you could say it works, but then you need a diesel fuel tanker from the sea, or basically lots of trucks coming and delivering new diesel fuel. And I mean, diesel suggests already what I mentioned when we talk about green energy, right? If you have here example of the Blendos campus I was alluding to on the earlier slide, which is Borealis data center here, just as an example, that can, going up to maybe around 100 megawatts. And they are sourced by two hydropower resources. But when, these would be going off, which is very unlikely, and they would use then diesel fuel, this would be very soon getting not anymore green and clean, right? And this is, of course, something which is usually prevented. And that's why this particular data center, as an example, would be interesting to think about, because they're two independent green energy resources. So that there's something happening with the energy resource is fairly unlikely. It also shows you that, basically for these data centers, you see quite an important factor. I cannot cover much in this course, but you see also for the marketing around it, not only the location is important, and of course the watts capacity that you may be interested in when you use data centers and want to host your racks in this data center. There's also certain certifications, you have to adhere to, adding to the complexity. So if you want to operate data centers your own in your own industry or in your company, these certification can be also quite elaborate, and sometimes even related to security. So man traps needs to be installed if you want to have certain ones or whatever. So this is a huge element on its own. So yeah, the power usage effectiveness is basically something you want to review as well. It's a factor that should be close to 1. Something you see here, Blendos, for instance, is something which is really 1.03. So this is something which is very, very good in terms of, usage of the effectiveness. And these metrics are, of course, very important for the data centers to get customers and so on. Then when you think about the whole cooling, again, when you want to create your own data center somewhere in the cellar for one company, good luck. You have to actually consider quite some other important stuff. And from this, you see a little bit how the circle works a bit. You would have, something which is normal air maybe going through racks, but you end up with lots of hot air. This is something then, of course, this depends now on the new technologies with warm liquid cooling, and there are, let's say, different aspects around, but the key problem remained that, basically the hardware will generate a lot of heat. You have even these days cooling options where the whole hardware is actually within water, so it's quite interesting. It's not really water, it's a very specific liquid, right? Not really water, but see here at second floor, for instance, you will notice is basically in very many data centers. So what you see here is just a fake floor. Essentially, underneath is much more here, this kind of second floor, where could be cables, where you could be the cooling infrastructure. It varies from the different aspects. But the key problem remains once you have put cold air through the racks, they will be heating up, and then you have some sort of cooling mechanism that put the flow back into the circulism and gets it cool again. And this could be one way of doing it. And the second floor is, I think, an important concept. Also, when you think here, the installation of UWorlds, this is another video I would recommend you to look in. There's, of course, many of the things I don't talk about. This would be network. Essentially, you see here, it starts all with a second floor, and then very quickly you will see many hectic people opening the second floor, putting lots of cables in. As I said, these racks are extremely well interconnected. So this is huge work as well. And there are different topologies these days, how you would do this. And of course, this is depending again on what you want to achieve in terms of a data center, what applications you have. Here's a FET tree structure, also alluding to the fact that if maybe one part fails, some of these questions, then some others could take still over some of the work. So it really depends also on what uptime you want to give. But of course, take away the message that the switches you see here in this, let's say, setup means also more payment, right? Switches are also a cost factor within all of that. I will say I give you this video here as a look if you want to, look at completion. At some point in time, you see the racks will appear. They will be positioned on that and then connected to the network. Think about that this whole hall is basically, I think, argon gas protected. So obviously you don't want to have sprinklers with water. So if there's a fire, then the gas will putting it out and leave some of these gentlemen here running around also, a live, survival percentage. So that they're not directly with the gas are, dead. Ideal conditions are, of course, before the fire, the people can run out. But, you never know what happens in such big data centers. So some of the gases are not completely lethal to humans, especially not, in the first couple of, time periods where they're exposed to it. But this shows you more and more that the data center is a very complex endeavor. And this is the idea of it. And it then depends also when you have the whole, let's say, idea of interconnecting these, then thinking about what we want to achieve with data throughput, right? You see also, we don't talk about here's a disk or there, you have large areas of storage disks, maybe connected also to some tape archives somewhere. This is still, of course, in practice when you have large quantities of data, petabytes. Remember one of the earlier course parts, then there's basically no other chance of going to tape archives. But you always have to think to migrate this somewhere close to the computing in order to get the good, let's say, throughput of computing, right, done. So there are lots of these aspects, which, is an important part for data centers, often overlooked, perhaps for people that don't know. And the scalability, which is now really the word which comes with the data centers, enabled in a way by economics of scale that it really works, is that there are different scalability factors we will briefly review before we close today, right? So, I mean, one of the things is really that you just want to go to data centers if you're interested in this, if you want to scale up. We talked about Angry Birds as the example, right? You have a couple of users, nobody's interested. Suddenly, bang, it goes, viral, and everybody wants to play Angry Birds. So your infrastructure needs to be scalable for this. So these people are interested. But if you have, let's say, a database which is always used every single day by one user, then chances are you better put a server in your own company. Right here, we talk about scalability is your requirement, and that's why you go to data centers usually. It's not the only requirement. You can also say data protection, redundancy. We have said replication, right? That might be another type of sort of scalability, however. So I think the size scalability is very obvious to you, hence where the name also came for shrinking up and down. Based on the demand, I can really increase suddenly very quickly my capability of storage, my capability of processing. Also with cutting edge GPUs, maybe if needed for AI, which wasn't there 5 years ago. So, and you don't have that in your cellar. So this is, of course, something which, is very nice. Then think about the whole ecosystem, perhaps as an example that you had from Apache Spark. The whole ecosystem, right? I want to have a Hive database. I want to have, basically Apache Spark in the latest, greatest versions across a different cluster. I want to have this connected with deep learning using PyTorch or TensorFlow. So you have lots of software that needs to be dealt with if you do your own data center in different versions that only play together in different versions, right? So if I may quote, say, a nightmare of different software versions that need to be deployed on all of these different systems, have to work together with different programming environment, different operating systems, different compilers, right? So someone in the HPC world will know Fortran, is still there, C is still there. So it's not only interpretation languages and Python everywhere. So hence, this is something where you usually get with data centers also very quickly a software scalability aspect. So you can switch more quickly to the newest version of Apache Spark if needed, and things like that. And we will talk about this also more in lecture 15 when we have this open stock cloud operating system, what sort of different parts enable you quickly as an operating system in the cloud to scale up with it. And then we talked about application scalability as well, of course. So again, you want to have different applications and running on this. You want to have not only different applications, but one application, as we said, for instance, Angry Bird is just used by one user, and suddenly, bang, it is actually increasing. So then you can very quickly go up and basically then scale with a number of users. Or let's say if you go into the Spark domain again, or Hadoop domain, as we will have also in lecture 8 and others, where you are interested in looking maybe at documents at high throughput. You have a kind of application that is counting words in newspapers, and suddenly someone gives you a contract with having not only newspapers but lots of magazines, and your orders of magnitudes of data is suddenly scaling from gigabytes to terabytes and potentially petabytes. So this is also where the application can relatively easy scale in this cluster, because you have also the necessary hardware around it, but also the mechanism of adding to the application, again, more, basically flexible data, and perhaps also the processing power. And then the technology scalability is, I think, very important for us to understand, particularly for AI. GPUs now, especially from NVIDIA, I'm not paid by NVIDIA, I should say, but it's one of the dominant technologies we have to agree on. And the NVIDIA generations that you have just seen in one of the slides, right, reaching from Kepler, where I did my first machine learning tutorials with parallel support vector machines on, now working on cutting edge chips with A100, H100, H200, and Blackwell soon, is an order of magnitude that it's so much advancements in technology, right? And this is not long time, right? This is something like the 10 years maybe from Kepler. Now, if you think about Ampere was still, cutting edge 5 years ago or 3 years ago in many of the different servers, and now there are very new, nice GPUs available. And if you now put this into the whole domain of switches, of networking as well, and also some improvements in the storage field, this means the technology scalability can much more adapt to new, elements that coming up. And by reaching perhaps a bit far would be also quantum computing, right? So in EuroHPC, we have already the first quantum computers. We deploy next, or basically in collaboration with the HPC systems. So next technology is in front of the door called quantum computing, right? So we do lots of publications with it. It's not mainstream like perhaps HPC becomes more and more. But this is another area of scale where perhaps in the future we see also Amazon and Microsoft more and more adding then these quantum computers to their scale. What quantum computers can do, for instance, they would be having here and there quite some impact in quantum machine learning when you do optimization, right? This thing where I said stochastic gradient descent. Some of the quantum computers can really put, let's say, water over the error surface and find the minimum much more quicker with a click of the finger in terms of time, instead of going iteratively taking derivatives and the old way, as we would say. However, quantum computing is in a way still in its infancy, but we have, if you want to look at the EuroHPC joint undertaking website, already several quantum computers, which shows you that the technology is never standing still, right? We're going already apart. People talk about quantum internet already, complete secure connections end to end and so on. But this leaves a bit the domain of the course, so we will not go into quantum computing a lot. Just at the end, some kind of other appetizers of the material that were coming up. And when we talk about infrastructure service, platform as a service, software as a service, why you would be interested in different layers there, something we will discuss. And also the motivation why perhaps some people would be still interested to create a small private cloud. Private means that essentially have it in-house, right? So hence we talked a little bit about, if you remember, the hospital use case, right? With patient data. This might be a perfect example where, you have these private clouds, and there's something very sensitive in terms of data that you never want to share it. It could be also governmental, right? So it should be not leaving, let's say, the country for some reasons, these kind of restrictions with some of the data. But for some reasons, these organizations also here and there want to combine it with public cloud. So public cloud is something you already learned now. We have talked about, basically the famous ones are basically shown here. And then there's something like hybrid clouds where you want to connect both of these worlds together to form your solutions. Let's say the hospital would always keep the data in itself, but for some applications in terms of computing, for maybe anonymized data, pseudonymized data, they maybe want to, work with the public cloud vendors to get an order of magnitudes of compute, which perhaps his own hospital cannot afford to create, right? Let's say lots of GPUs. And these are topics also fueling this data centers industry again, this kind of hybrid clouds and the idea that goes along with it. But I think you get the idea very quickly with this. And with this, we're also at the end of the course today. I still encourage you to look inside this, video. It's an interesting way, again, having come back to many of the things we discussed, failure, and you see here already the many racks, the many technology deployed there to form a data center. And I hope you have now a much better idea how complexity is really, driving this. And of course, giving us a nice opportunity these days because data centers to operate them alone in your cellar is something I would not really recommend unless you're really a very large company. But yeah, even then you may reconsider using professional data centers. In this, and we end with lecture 4, and we will continue with lecture 5 next week. So have a good weekend. Talk to you soon.